I'm just going to tell you briefly about what I've been doing at LSU along with many bright graduate students. So these are the students I'm working with. Siddharth actually just defended and unfortunately couldn't make this event because he's now in Poland visiting the Hordesky family to collaborate on topics in quantum information. And then he's going to start a postdoc in Belgium with the group of Nicolas Serre, thinking about intersections of quantum optics and quantum information. So unfortunately couldn't make it. And then I've been working with Anid. I'll talk about a project I did with Anid and Siddharth. Anid is right here. And then Kunal will actually speak today. Kunal's right there, talking about some work that we did on characterizing continuous variable quantum gates for quantum computation. And Sumit and Vishal also talk about what they've been doing. And this is also sort of the order, Siddharth graduated, maybe Anid will be next. This is an awkward conversation. And at some point I'll figure out what Sumit and Vishal are doing. No, I'm kidding. You can send me your topics so we can put it on the website. Presumably it's just quantum information and computation like everyone else. Okay. So, good. So what do I think about? I gave a tutorial last night that some of you attended, and thanks for showing up for that. Maybe it was for the free tacos, I don't know. So the main topic that I think about is communication capacities, sort of continuing the ideas of Shannon, but in the quantum domain. And there's all kinds of problems that arise having to do with communication. You might be interested in sending ordinary classical bits over a quantum channel, and then are there benefits are there gains by incorporating quantum effects? And so in principle, the theory tells us yes. And then motivated by quantum key distribution, you can think about the private capacity of a quantum channel, so how many private classical bits can you transmit? And then motivated by quantum computation, concerns there, perhaps with distributed quantum computing and quantum networks, which is a topic that's gaining momentum more recently, you might be interested in the quantum capacity. And then there are other ones. This LOCC assisted is very important as well. LOCC means local operations in classical communication. So it's really, when you're communicating over a channel, you allow them classical communication for free, which is what we really do in quantum key distribution. Okay? And in particular, I'm very interested in bosonic Gaussian quantum information. This is the core way that we intersect with people working on quantum optical experiments. We sort of think about the theory and incorporate models of bosonic communication channels and figure out how much data you can send related to these different kinds of capacities. Okay, so those are some pretty important topics. I managed to survive with funding by working with teams on quantum key distribution. So that's ended up being a pretty critical topic as well. And from a fundamental perspective, I've thought about quantum entropies. This is how we quantify information, and how can you refine and understand these entropy inequalities. So that's been an important topic as well. Related to quantum communication is entanglement theory. How do you quantify entanglement? There are various measures for doing so. And so we've thought about various entanglement measures quite a bit. And if those entanglement measures can be applied to these applications of private communication and quantum communication. And then a topic of increasing interest in the larger community is this notion of a quantum resource theory. So that was motivated by entanglement theory. And, entanglement theory is an example where you say, okay, I allow some things for free, right? So I allow the ability to make separable unentangled states for free. You have some set of free operations, which would be local operations in classical communication. And then anything that's not free is a resource, and then you use this kind of framework to understand entanglement theory. But you can apply this to many different domains. You can apply it to thermodynamics. You can apply it to quantum computation. It's a funny name, but people have called it the resource theory of magic. So there are these states that enable universal quantum computation, and the name given to them by Alexei Kitaev, who's a big shot, he called them magic states. So then that's what we call them. So magic states enable quantum computation. If you don't have magic states, what are called Clifford or stabilizer operations, those are considered free, and they don't enable quantum computation. So even though you can have highly entangled states that come about from Clifford operations, C naughts and Hadamard's, you don't get any advantage over classical computing. And so that resource theory has become more important recently. I've been keeping track of the time, but I'm not keeping track of my own time. So someone has to keep me on time, and maybe that should be Ryan. Okay. So this is a paper that I worked on with Anit and Siddharth. Maybe this was a year. I don't know. This was a long project. But we ended up proposing a new resource theory that generalizes entanglements, and it has to do with extendability of quantum states. Okay, I'm not going to say what that is because there's not time, but thinking in such a way allowed us to obtain tighter bounds on quantum communication rates. So there's a simple model of quantum communication called the depolarizing channel, and we were able to establish tighter bounds on how many qubits you can store in a device that's subject to this depolarizing noise. Okay, so this KDWW is us, so we improve the bound. Unfortunately, it makes a more negative statement because we're saying, oh, actually the limit is much more severe than what the previous work thought, but still, it's good to know the fundamental limits. So that's something we think about a lot, is like, what are the fundamental limits? That's a really motivating, driving question. Okay, that's something we did, and it's still in review. This is a paper that Kunal and I put up recently. We're actually motivated by Quilt to get this online. So Kunal worked really hard for many days, many nights, and we put this paper online. And Kunal's going to talk about it much more later, but it's about how do you characterize the performance of a continuous variable quantum gate, right? So this is, in quantum optics, an operation that you're interested in implementing in the lab is a displacement operator. So this is a displacement of the state and phase space. And then the most common experimental approximation of it is, well, you just send in the state that you'd like to displace. You interact it with a bright, coherent state in a beam splitter, and then you just forget about this mode that comes out, and then this mode gets displaced according to the parameters eta and beta. And so that's the most well-known approximation that's used, and so we characterized how good that approximation is using various kinds of norms or fidelity measures. Okay. This is meant to show off a paper with Siddharth and Sumit. Sorry, this is published now in Journal of Mathematical Physics this year, and this was sort of mathematical physics work. That's why we published it there, just about understanding entropy dynamics in quantum systems, and so it's related to these entropy inequalities, which was this core topic that I mentioned. Okay, and I'm really just trying to flash something from the paper, and this is some theorem that tells you limitations on entropy change in a dynamical process. Okay, so I'll just leave it at that. And then the last thing I'll talk about is a work that's also in review. This was a joint work with Vishal. This was a project that spanned a long time as well. It started, Patrick and I were at a funding review meeting, and maybe we got slightly bored, and so then I said to Patrick, why don't we think about entropy uncertainty relations, and then we did that, and then this project came from that. So what we did was in quantum mechanics, there's this famous energy time uncertainty relation, and what we did was to reformulate it using entropies to quantify uncertainty. And then we characterized the energy time uncertainty in a way that you can think about it in terms of a game. Okay.